Is that okay? I think that's good lighting, right? Okay, welcome everybody to our Monday Colloquium, November 7th here. It's my great pleasure to introduce Andrea Lopez-Lang, who I've known for almost 20 years now. It's amazing, isn't it? And she still looks like she's 18. I don't know how that happens. But Andrea was an undergrad here, came from the Washington, D.C. area. Was it the Jefferson Science Magnet School outside in Alexandria that you went to? And so Andrea came there. I think I'm right. You didn't know you wanted to be an atmospheric scientist, but very sharp individual, was into things and finally decided on atmospheric science. Also decided, you know what, I'll walk on in the track team, and became captain of the track team. A chancellor's scholar, the whole bit, just an outstanding scholar from a young age. And then decided to stay here for a PhD, which scared me to death actually, because you know when you have really talented people and you don't want to let them down. But Andrea made it easy. I didn't have to do anything. She just started looking at upper fronts in the lower stratosphere and discovered all kinds of new things about them and got a lot of people excited about those ideas. And then ended up at a postdoc at University at Albany. I think you left in 2011 for that, you said, right? Yeah. And then the next year started a faculty position there, and that's where she still is working. And no longer on upper fronts, but into the lower stratosphere. Andrea is, I wish I had known I was going to do the introduction. I would have had the long list of all of the various panels and workshops and then working groups that she leads, but she's done all kinds of different things in terms of stratospheric, tropospheric interaction, S2S prediction, and S2S strategies for prediction. It's just a long, long list, and my introduction doesn't do it the justice that it well deserves. All of this in a very short time, in a career that's just exploding. So it's a great opportunity for us to have Andrea back on campus. If you don't know that already, she's up in
1531.
1531. That's temporary, but for now, because she may move to another office, but Andrea Lopez-Lang is back, and that's good for all of us, let me tell you. And today she's going to be telling us about the dynamics and predictability of winter extremes, a subject that I have a little bit of interest in, as some of you know. And it's so great to see a person with whom I've had a scientific and personal relationship with for so long, coming back, telling us about things that I don't know anything about. I just love that. So I'm really excited about this. And Andrea, take it away.
Thanks, Don. I think step one is to turn the microphone on. There we go. So thank you, John. I am really excited to be back here, and since I am now on campus and upstairs, I decided to take a slightly different approach to thinking about your traditional colloquium. And since I'm here, I want to really use this opportunity to tell you about me and the things that I'm interested in and some of the things that I'm working on, so that maybe if you see something interesting, you can come upstairs and have a conversation with me, and we can talk about it in more detail. So yes, I'm here. I'm talking about the dynamics and predictability of winter extremes. And so to do that, I want to start by really thinking about what we're talking about when we're talking about winter extremes, and then we'll get into the dynamics and predictability of them. So to start with, maybe some of you have seen this, but US billion-dollar weather and climate disasters. NOAA has really started to take a really good inventory of what these are, so that as an enterprise, and I say enterprise, I'm talking about weather and climate scientists from the academic side, people working in the private sector on the industry side, people working in the public sector on the government side, really, how are we influencing as a community things happening in the broader space of the economy, of society, and really how can we be involved in those discussions? So US billion-dollar weather and climate disasters from 1980 through today, there have been 338 of them with over $2 trillion in impacts. And associated with these 338, there have been a number of fatalities. So, you know, here we're looking at it in dollars and fatalities, which is a really bad way to look at this in reality. But from a snapshot, it tells you that it has both economic impacts, societal impacts, impacts on livelihood, and you can clearly see that these are things that, as you all are in here, know that we need to pay attention to, and we need to be able to communicate and talk about these things. So if we're thinking about billion-dollar disasters just from last year alone, from 2021, we're thinking about a variety of different impacts. And so you can go and you can look at this. NOAA has this online right now. You can go look at a big table with this information. But if you look at 2021 billion-dollar disasters, you'll see a variety, including wildfires in the west, severe weather in the central part of the country. And if we take a look at these, I want to emphasize some of the ones that happen in the winter season, because these are the winter extremes. So December 10th, a very large severe weather outbreak, not your typical severe weather season, but it happened in the wintertime. And we know that there's a very large scale setup that gives us these severe weather outbreaks. We're not just talking about one line of, one thunderstorm complex. We're talking about a swath that impacted multiple states, multiple regions, had huge impacts, $4.1 billion in damages, nearly 100 fatalities associated with it. So this is a winter extreme, and when you think about winter extremes, you may not think about tornado outbreaks. Another one is flooding. January 26th through 29th, there was a major flooding event in California. I don't know if you remember, there were big pictures of Highway 1 washing away. That's the coastal highway. Associated with that, there was high impacts on society and damages. And then probably the biggest one that we all are familiar with, the one that got a lot of press, was the big cold air outbreak, winter storm that impacted Texas, and a variety of other parts of the central US. At one point, there was over 10 million people without power. You can imagine large societal impacts associated with that, $25 billion in estimated damages to date. So a huge variety of different types of weather and climate events associated with the winter season. And so I'm really interested in the winter season from a dynamics and predictability aspect, because wintertime dynamics are different than summertime dynamics. So when we're thinking about extremes in winter, we're thinking about not just winter storms, we're thinking about a variety of different types of impacts and events. And if we actually break down these billion-dollar disasters, and we think about the ones that happen in the December through March timeframe, if we think about all of these different types of disasters that NOAA keeps track of, you can see that the highest count of billion-dollar disasters comes from winter season severe weather. Not winter storms or freezes, but severe weather outbreaks. You can also see that flooding in the wintertime is a big, high impact event. So, usually we think about wintertime, we think about winter storms and freezes. This is a subset of the types of high impact events we're thinking about. Okay, so with that background on winter extremes, I feel like I can start over again and now present the dynamics and predictability of winter extremes. I'm going to also include pictures of my current research group. These people, my grad students, are really working on these projects, and two of the projects that I want to tell you about today are assessing the influence of lower stratospheric Rossby wave dynamics on thinking about winter extremes in North America, and then also a project funded by the Office of Naval Research on understanding the role of the stratosphere in subseasonal to seasonal variability and predictability of Arctic weather systems. So this is really extratropical dynamics, and we're thinking about extratropical both being mid-latitudes and Arctic region, and also thinking about it on time scales that are subseasonal. So why subseasonal? So if you have been thinking about, impacts, these huge extremes having both economic impacts and societal impacts, when we're thinking about this, if we want to mitigate against some of these worst impacts, we need to have time to prepare for the worst of the impacts. So traditionally, in thinking about weather and climate, we've partitioned the predictability and thinking about forecasts in the weather and climate space. So we have weather forecasts that are really thinking about weather warnings, weather watches, sort of short term, being a week or less prediction, and communicating risks at a week lead time, sort of on the extended range. Or we can think about climate forecasts. We know that there's climate outlooks that are produced by the Climate Prediction Center. We know that There's a lot of climate modeling talking about things from, decadal timescales. But this space in the middle is where a lot of decisions that impact society are made. And so this space happens to be that subseasonal to seasonal timescale of about 2 weeks to 2 months to a season. And it's in this timescale that a lot of decisions in a variety of different sectors are made. So if we want to, as a weather and climate community, discuss these, we need to sort of think about what we're talking about. So when we think about weather and weather forecasts, we're thinking about predictability coming from our really good observations, coming from really good initial conditions, and having forecast models that are able to ingest these and make forecasts based on this really good subset of initial conditions. Thinking about climate forecasts, really we're thinking about predictability from the Earth system, from a variety of different variables that impact the boundary conditions, the cryosphere, the ocean, and even the stratosphere. From a subseasonal to seasonal timescale, really we're thinking about both of these things together. And we're trying to capture the slowly evolving variability that comes from some of these slowly evolving phenomena, like things like the MJO or the stratospheric variability that can happen on timescales that are longer than weather but shorter than climate. So on the decision perspective, and we think about decisions in different sectors, I've tried to highlight here with the different colored bullets, trying to fit into the weather to S2S to climate timescales. But different sectors think about decision and planning at these same timescales, and now we can start to fit in the types of forecasting or outlooks that go into these different decision timescales. So for example, the energy sector, at climate timescales, we're talking about where do we place wind turbines? Where should we put new solar fields? But at the subseasonal timescale, now we're talking about management and allocation of resources. We're talking about planning for spikes in demand. And at weather timescales, really we're talking about immediate managing of energy infrastructure. So the subseasonal timescale, there's a lot of important decisions being made that have impact both on society but also can mitigate against the worst of the economic damages. And of course, recently in the last decade, a lot of people have come to realize this. And there's been, for example, the Weather Research and Forecasting Innovation Act was passed by Congress in 2017 and has a large chunk of it devoted to better S2S prediction and really understanding S2S. NOAA had the S2S prediction task force that really focused on bringing people working on a variety of different aspects of S2S prediction together to really sort of organize thought and ways to move forward in this space. And then also, under the World Meteorological Organization, they currently have the second phase of the International S2S Prediction Project happening that is providing an organized set of data for researchers to use to actually tackle some of these projects. So from a dynamics perspective, there's a lot going on, and there's a lot of things interacting. And so this is a quick snapshot. I'm not going to go into the detail of this, but there's a lot of different slowly evolving phenomena that we can use to provide us sort of information at that subseasonal to seasonal timescale. And if we think about this, this is actually the background of this figure is the temperature anomalies from February 2019. And so if you look at this over North America, especially over Canada, there was a cold air outbreak that was developing during this period. And there were a lot of things contributing to that cold air outbreak. Think winter extremes. We had blocking in the Gulf of Alaska. There was wave-breaking events downstream. There was stratospheric polar vortex. There was some extremes happening there. And so all of these pieces fit together to give us an increased likelihood for extremes to happen. And so this is what our research group is working on, and we're really focused on the anomalous stratospheric conditions and how they can modulate the background tropospheric flow to increase the likelihood or decrease the likelihood of these synoptic scale setups to winter extremes. And these are the things that can extend predictability beyond the medium range to increase or decrease the likelihood or probability of an extreme event. So, what I want to do is give you an overview of some of the things that we've been thinking about in my research group. And so we'll start with stratospheric variability in the tropics. So when we're thinking about stratospheric variability in the tropics, one of the things that is one of the most predictable oscillations in the atmosphere is the quasi-biennial oscillation, the QBO. And it's a downward propagating oscillation of the zonal mean winds in the equatorial stratosphere. And there's an oscillation in these winds going from zonal mean easterlies to zonal mean westerlies of about 28 months. And these easterlies and westerlies descend with time. So not only do you have a wind speed maximum or minimum descending with time, you have a shear zone associated with that descending with time. So what you're looking at here is a time series, a vertical time series of the structure of the zonal mean winds, starting in 1980, going in through current from NASA. They update this regularly. But everywhere you see the brown colors are westerlies, starting at 10 hectopascals, descending with time. Everywhere you see the blues, that's easterlies, zonal mean easterlies. And associated with this, we have zonal mean winds, and we have these shear regions. And in the shear regions, there's temperature anomalies associated with the QBO oscillation. So not only do we have zonal mean easterlies or westerlies descending with time, we also have colder and warmer regions descending with time. And that can impact the tropopause region in the tropics from a convection perspective. But what we were interested in was trying to understand how this might impact the extratropics. So there was a really nice review paper that, if you're interested in the QBO, I highly recommend this review paper by Gray et al. In 2018. But they summarized the 3 theories on how the QBO at subseasonal timescales can impact the extratropical region. So I know that there's a lot going on here, but the takeaway is to look at the colors of the different arrows. So basically, they said, they summarized all of the literature, and that there's a blue arrows point to a polar route for the QBO in oscillation in the tropical regions to impact the extratropics. And through that, the interaction in the zero line in the subtropics impacts where Rossby wave breaking occurs and where Rossby waves can and can't propagate. That can impact the stratospheric polar vortex, which can impact the mid-latitudes. There's a subtropical route in which the thermal anomalies of the QBO can impact the subtropical jet, and that can impact Rossby waves from the subtropics and high latitudes, how those interact at the tropopause. And then there's a tropical route that has to do with the deep convection and how that deep convection oscillates when you have the cold anomalies or warm anomalies or easterlies or westerlies reaching the tropical tropopause, and that can impact the overturning circulation in the subtropical tropical regions. So the QBO, even though it's an equatorial stratosphere oscillation, can have its fingerprints in the mid-latitudes. So one of the things we were interested in my group was seeing if we could actually diagnose this relationship in extremes in the mid-latitudes. And so to summarize, this was a whole project in itself, but to summarize the results, is we looked at the most intense cyclones in the extratropics that lasted 2 days, had lengths of over 1,000 kilometers, with sea level pressures that deepened rapidly, that met the bomb cyclone criteria. And so in the MIRA-2 data set that we looked at, we had 2,800 of these bomb cyclones. And we did an analysis on them, but one of the key results that we saw is that if you look at these bomb cyclone track differences between the easterly and westerly phase of the QBO, we see noticeable differences that are consistent with the literature that talks about storm track changes and some of the larger scale, just tropospheric changes by themselves. And so one of the biggest things that we saw is that during QBO westerlies, we saw enhanced bomb cyclone tracks in the high latitude part of the North Atlantic. And so this was really interesting because if you're trying to understand winds and sea ice distribution moving into the wintertime, these bomb cyclones are going to be the ones with the strongest sea level pressure gradients, the strongest winds that can do the advection of sea ice. So this was something that we were interested in, and is something that we're still working on, diagnosing some of the dynamics associated with it. So this is the impacts of the tropical stratospheric variability. Our group is also looking at extratropical stratospheric variability. And so from that perspective, we're thinking about understanding from the stratospheric polar vortex. So we're trying to understand impacts of the extratropical stratospheric variability. And to think about the polar vortex, we're really thinking about the stratospheric part of the polar vortex. So during the winter time, as we have radiative cooling over the high latitudes, we get really cold temperatures over the high latitude stratosphere. Strong temperature gradients develop from the sunlit areas to the non-sunlit areas. Thermal wind tells us we have to develop a jet in the stratosphere. So this is our stratospheric polar vortex. The strongest winds associated with that typically are about 60 degrees north latitude, and under it is where we have our polar jet stream. Polar jet stream, not always at 60 degrees north latitude, a little bit further equatorward, but these two can interact. So when we have strong polar vortex conditions, we're talking about very strong zonal mean westerlies at about 60 degrees north. And usually the polar vortex strength is measured at 10 hectopascals and 60 degrees north by the zonal mean wind. And if we look at it from a very conceptual, what I could do in PowerPoint perspective, we're thinking about the polar jet stream at the tropopause interacting with the stratospheric polar vortex. And when we have very strong winds, there's a reduction in the wave activity that allows these two to communicate. And so a lot of times what that does is, because of the reduction, it keeps the coldest air via thermal wind relationship in the high latitudes and reduces the frequency that we get these extreme cold air outbreaks. And so that's what happens during typical strong vortex conditions. And if we actually do the work to look at a climatological data set, we can look at the weekly sea level pressure and temperature anomalies associated with strong polar vortex events. And what you're looking at here is, I know these are kind of small, but these dashed lines are the sea level pressure anomalies. The color contours, warm corresponds to warmer than normal, blue corresponds to colder than normal. And you can see that during strong vortex events, typically we see the extratropical regions being warmer than climatologically normal, being that these conditions have a very strong vortex keeping the coldest polar air in the high latitudes. When we have weak stratospheric vortex conditions, the opposite is true. We have a very disturbed polar vortex, and during these disturbed polar vortex events, we still have our tropopause jet. Usually we have high amplitude flow along the polar jet, but there's increased wave activity that allows the waves in the troposphere to communicate with the waves in the stratosphere. And what this does is, via eddy driving, it forces a reduction in the stratospheric zonal mean flow. So during the weakest events in the stratosphere, we have sudden stratospheric warming events. So we have reduced temperature gradients via thermal wind arguments. We actually have a reduced meridional circulation. Subsidence in the high latitudes, we get warming, and associated with that, we get our sudden stratospheric warming that's associated with the warming in the highest latitudes, easterly winds in the high latitude polar vortex region. And so associated with this, we see tropospheric impacts that are associated with more cold air outbreaks. This is the surface temperature anomalies in the 60 days after a composite of 37 SSW events. We see the strongest cold signal in Eurasia. We see a little bit of a cold signal in North America. Canada is actually, eastern Canada is warmer than climatologically normal. Associated with sea level, what we see in the 60-day composite is an increase in low pressure in the North Atlantic, and this is really associated with a shift in the storm track, the North Atlantic storm track. So we see a southward, equatorward shift in the storm track. Regions, especially over southern Europe, see more increased precipitation, flooding, and that sort of thing in the period after SSW events. So from a dynamics perspective, we know that these events can have impacts on subseasonal timescales. So if we're able to resolve them and able to use this information from a prediction perspective, maybe this is where we can start helping decision makers mitigate against the worst of the extremes. So from a dynamics perspective, how do these happen? Well, if we think about this, most of the stratospheric variability has a source in the troposphere. There's an interaction between waves along the tropopause, the extratropical waveguide, and we can have an anomalous wave source be amplified right at the tropopause, and via a vertical propagation of these Rossby waves, and the vertical component of Rossby wave propagation is proportional to the eddy heat flux. If we get these Rossby waves to have a strong vertical component to their propagation, as they propagate vertically, they amplify in the stratosphere, and eventually, sometimes, not all the time, but sometimes these Rossby waves break, and they can deposit easterly momentum in the stratosphere along that stratospheric polar vortex. So this wave dynamics is what forces that breakdown of the stratospheric polar vortex. And once this happens, once we have this anomalous easterly momentum deposited in the polar vortex, we can have this downward signal into the troposphere. Yes?
I was just wondering, are there preferred zonal wave numbers that are
Yes.
allowed in step 2 in this diagram?
Yeah, absolutely. So the question was, are there preferred zonal wave numbers for this? Well, it turns out that the lower stratosphere is a filter to pretty much wave numbers greater than about 3 or 4. So it's mostly the planetary scale waves that are able to do the breakdown in the stratospheric polar vortex. So there's definitely a seasonality to this. The polar vortex is only westerly during the winter season. It's easterly in the summer. So none of this happens during the summertime, which is why I'm interested in wintertime extreme events. But another interesting thing about sort of the step 1 through 3 is that because it is wave driven, the predictability we've discovered is really only on synoptic timescales. So this is a really, sort of rough, if you're really trying to help people make decisions, this is really hurting us. And we did an analysis on this to look at the predictability of these extreme stratospheric events. And so there was a bunch of us that contributed to this big review paper and analysis of the predictability of the stratosphere. And we looked at a bunch of different types of stratospheric variability, and we looked at how well we were able to predict these events at subseasonal timescales. And it turns out that everything from the midwinter sudden stratospheric warming events, early warming events, these are warming events that don't quite meet that easterly reversal of the zonal mean winds, but still are associated with impacts in the troposphere, strong vortex events, negative heat flux events. These are sometimes linked to strong vortex events, but not all the time. All of these, even final warming events that are a climatological feature of just the stratosphere, the predictability, and here we're looking at the percentage of ensemble members for a different variety of subseasonal forecast models, the percentage of ensemble members that were able to capture the event within a plus or minus 3-day window of it actually happening. And you can see that we don't reach that 50% threshold until synoptic timescales for most of these cases. So this was sort of, we thought we might see this, but then when we actually did the analysis and saw it, it was a little bit disheartening. But at the same time, some of these models, for example, the Bureau of Australian Meteorology model, I think JMA, some of these models at S2S timescales have very low tops and aren't able to resolve some of the features that have happened in the stratosphere. So that's one thing that is slowly changing about making predictions at this timescale. So what happens is, yes, we only have synoptic scale predictability for steps 1 through 3, but it's steps 3 through 5 where we have our subseasonal predictability. So once we are able to resolve this happening, that's when we get the subseasonal ability to make predictions. So there was a review article about all the ways that the stratosphere impacts extremes in the troposphere. The print is very tiny and you can't read this, and that's sort of the point, is that there are a variety of different ways that different phenomena in the stratosphere can impact the troposphere. And it can not only impact, precipitation and that sort of thing, but there's very specific regions where some of these impacts are seen. And that's another key point, is that this isn't a generic, if this event happens, it happens everywhere. It can happen regionally. So this is one of the things that we're trying to work on, is the events and the regional impacts. So SSWs are shown to increase the likelihood of cold air outbreaks by 50%. If an SSW happens, there is an increase of 50% chances of having a cold air outbreak somewhere in the northern hemisphere. Where that is, it can be a little bit different for every SSW. So understanding how they're all different really has implications on how we communicate the extremes. Cyclone tracks are impacted by SSW, sudden stratospheric warming events. Wind extremes are also impacted. So it turns out that in Europe, there is a large community interested in the energy sector of what's going on in the stratosphere, because wind extremes and wind generation in the wintertime over Europe can be impacted based on the stratosphere's variability. So there are teams of stratosphere dynamicists that work for energy companies, which is really interesting. All right, so if we're interested in the impacts of extratropical stratospheric variability, our group is really interested on the US impacts from temperature. So what we're looking at here is we're looking at a time series of the zonal mean winds in the stratosphere, and this gives us a good approximation of the strength of the stratospheric polar vortex. So what you're looking at here is the 2018-2019 zonal mean winds in the stratosphere. The red line shows us that we started in July, we have easterly winds in the stratosphere, they go to westerly, and then midwinter we have this rapid decrease in the zonal mean winds associated with one of these sudden stratospheric warming events. So we just said, we did all this analysis to show that SSWs can impact the mid-latitudes and increase the likelihood of cold air outbreaks. So then the question is, well, there was a cold air outbreak in the central US during this period. Are these two actually related? Can we say that this cold air outbreak happened because of this SSW? Did it increase the likelihood? Are they related? So this is a question that if you really want to think about some of these ideas, we need to be able to have an answer to this. So this is the composite view of the impacts of these 37 SSW events. There shows maybe a cold anomaly, but it's not statistically significant. So are these related or are they not? So one of the things we're doing is we're trying to look at SSWs from a different perspective. The way that they've traditionally been looked at is a deceleration in the zonal mean winds, and thinking about it from a zonal mean perspective to measure the stratosphere. But one of the things we're doing is we're taking a non-zonal perspective, and we're trying to actually track the location of the stratospheric polar vortex and see how anomalous it really is, and understand if the variability of the vortex can tell us something about the types of impacts we might expect. So what we're doing here is we're looking at the 10 hectopascal geopotential height, and I've highlighted the 30 kilometer 10 hectopascal contour is this dark or bolded black contour, and then we use a best fit ellipse to track the vortex. And so in this, we can actually quantify the location, the size, the strength of the vortex by thinking about a couple of different variables associated with the vortex ellipse. And so we can track its latitude, longitude, its ellipticity, so is it elongated, is it not? And then we can start to say things more concretely about how the geometry of the stratospheric vortex variability impacts the troposphere. And so one of my students is working on this. And what she's done is she's started the process by looking at the Kendall-Tau correlation between each one of these vortex metrics with cold in the US. And what this, we're looking at the 10 hectopascal zonal mean wind correlation to temperatures over the central US. And then we're also looking at the latitude, the rotation angle, the ellipse area, and the ratio, and how that's related to temperatures over the US. And what we found is that each one of these metrics has a slightly different signature in how it's related to temperature over the US, and that some of these look very similar to the zonal mean wind perspective, some of them don't. And what we're hoping to do is use all of this information together to make more informed statistical predictions about temperatures at extended timescales. And so we're applying these ideas to S2S forecasts to sort of use a statistical dynamical approach to thinking about temperatures over the US. So this is one project that we're working on. Now, this is trying to think about temperature extremes, but in the US region, but we're also interested in thinking about how the stratosphere impacts extremes in the high latitudes, in the polar regions. And so as another project, we're thinking about, as part of this larger initiative, overcoming barriers to extended range prediction over the Arctic, the Navy is really interested in how Arctic cyclones can move around sea ice, where the wind is going to be, because that has implications for operations in the Arctic region. And what we're doing is we're considering these features called tropopause polar vortices, which are PV anomalies near the tropopause that meander around and can have lifetimes of weeks. And we're interested in considering these TPVs as precursors to Arctic cyclones. And if we can use the variability of TPVs and their associated properties and think about how they're related to stratospheric variability, maybe we can say something about the predictability of surface cyclones in the Arctic using these TPVs as sort of the middleman, if you will. So we're trying to understand if there's a relationship between these tropopause vortex features that happen at mesoscales and variability in the stratosphere, and if we can use that to talk about how maybe some of these cyclone track differences show up in the SSW impacts perspective. So when we're thinking about these tropopause polar vortices, they're long-lived features. They can have lifetimes of weeks. They're radially maintained. So once you have the vortex maintained, locally within that vortex, there's a sharp vertical water vapor gradient right at the tropopause. That gradient has implications for the vertical profile of heating, which then has implications on the PV generation. And we can generate enough PV to maintain these vortex features in the high latitudes. They're generally synoptic to sometimes mesoscale features, and they have their highest amplitude. The vortex itself has its highest amplitude right at the tropopause. And if we look at this is potential temperature on the dynamic tropopause, the 2PVU surface, and it's color-coded. It looks better on my laptop than it does here, but it's color-coded to really emphasize sort of the Arctic tropopause and the mid-latitude tropopause. And everywhere we see these little cold spots on the 2PVU surface, these features are these TPVs. So they're really cold, low depressions in the tropopause, and they can last in the high latitudes for weeks. So as soon as you have this vortex right at the tropopause, these can meander, but they don't always have a surface signature. Sometimes the idea is that these TPVs could meander over the sea ice edge where there might be a baroclinic zone, and maybe that spins up an Arctic cyclone. So these TPVs, if you were to take a cross-section through them, and Cavallo and Hakem did this, they're associated with tropospheric cold dome. They're associated with cyclonic circulations around them. They're associated with a PV anomaly, where we have our maximum PV in the lower stratosphere, and a sharp water vapor vertical gradient near the tropopause. So associated with this, these are dynamical vortex features right at the tropopause layer, at the interface between the stratosphere and the troposphere, and they are precursors to surface cyclones. So these features, if they're impacted by stratospheric variability, can have impacts on surface cyclones or other features. And a grad student led a project at Albany looking at these TPVs and looking at the track density of TPVs during North American cold air outbreaks. And what he showed was that in North American cold air outbreaks, there is a likely a 70% chance that you will have a TPV meander through this region during one of these cold air outbreaks. So he showed that this cold dome in the TPV can sometimes be the cold air in the cold air outbreak. So what we're interested in is we're trying to understand if the stratosphere can impact the variability of these features. And so one of my students right now is working on his dissertation thinking about these, and this is what he showed. So he partitioned this large data set of TPVs that we have. So there's something like 15,000 TPVs since 1980 that we've tracked, looking at cold season only. And we've partitioned the TPV tracks into strong vortex periods, weak vortex periods, and then sort of neutral vortex periods. And what we saw was that there is a major difference in the concentration of these tropopause polar vortices during different background states of the stratosphere. And there is an increase in TPVs in sort of the Canadian, North Atlantic, and into the Barents and Kara Sea region during or a reduction, during weak vortex events and an increase in the Bering Sea and Chukchi Seas during strong periods. And so we broke this down to look at, is this just a nice transition as you go from strong to weak? Is it a nice sliding transition? Or does one thing happen during weak vortex periods and a different thing happen during strong vortex periods? And that's what we found. So during strong vortex periods, we see a reduction in TPVs sort of set over eastern Siberia, Bering Sea region. And during weak vortex periods, we see a reduction in TPVs in pretty much the Canadian and high Arctic regions. Okay, so in my last bit of time, I want to think about a couple of different things. So we've been talking about the impacts of high-latitude polar stratospheric variability and its impacts on the mid-latitudes. So now we want to focus on just cold air outbreaks. So I mentioned at the very beginning of the talk the cold air outbreak of 2021. If we look at what actually happened in February 2021, what you're looking at here is the 1,000 hectopascal temperature anomalies daily averaged for all of February, going from the first week of February and so on. And what you can see is this cold air outbreak in February 2021 really lasted an extended period of time. And you could really see the signature start in Canada, and that cold air migrated into the US and persisted. Now, from an energy sector perspective, the cold air had huge record-breaking impacts on the energy sector. We're talking about record-breaking winter energy demand. Generation was really brought to a standstill for both renewable and fossil sources. And we had an energy emergency alert, which I didn't know existed until this event, of level 3, which is the worst of the energy alerts possible. Basically, that means there's going to be rolling blackouts that are put into place not because a power line fell over, but to really conserve the grid. So they turned off the energy to the grid during this event in 2 regions. So the energy grid is managed by different sources depending on where you are. There's ERCOT that manages most of Texas. There's a Southwest Power Pool that manages sort of the central part of the country. And both of these regions that manage power grids in those regions, had to have these rolling blackouts to preserve not only their grid themselves. There was a lot of other things going on that go beyond what I'm interested in. Well, I'm interested in my expertise. But it had huge implications for energy over a large part of the country. So if we're trying to make predictions for this event, and we look at the S2S models, if we think about this region in the central part of the country where a lot of the power grid was impacted, and we think about the cold there, the black line is the temperature anomalies in this region from the ERA 5 data, and then these squiggly lines are different forecasts initialized at different times in January that are all S2S forecasts. So the ones that are kind of purpley are ECMWF forecasts. The ones that are yellow to brown are the JMA forecasts. And then Environment Canada is the blue colors. The more muddled they get, the closer to the initial, or the closer to the event they are. But the takeaway is that at S2S timescales, none of these really captured the extent of this cold air outbreak. And if we look at it from a perspective of how many, if we expand this to more models, what percentage of ensemble members were able to capture a minus 1.5 standard deviation event? Really, it's only the ones in week 2 that were able to signal this event. So what was going on? Was the stratosphere involved? Did we just miss this event? This is another question we have. And we started to think about this because if you look at February 2020, there was a cold air outbreak. It didn't have the impacts that this one had, but the setup was very similar. And if we look at this, so it's meant to be a little bit blurry from the back because what I want to emphasize is this is 2020 and this is 2021 during this big cold air outbreak event. I've highlighted the 0 degree Fahrenheit isotherm, the freezing isotherm, and I've highlighted a couple synoptic features. So we have a cyclone moving off the east coast. We have an anticyclone over the central part of the country. But if you were to look at these two maps, they look very similar in terms of where the cold air is, where we have northerly flow, where we have a surface cyclone. So these two cyclones look synoptically very similar. One happened during a strong vortex event, one happened during a weak vortex event. How can we be talking about the role of the stratosphere when things look like very similar? So this brings us to the last thing that my group is interested in, is thinking about a different type of stratospheric variability known as wave reflection events. So a wave reflection event has been shown recently in this Matthias and Kretschmer 2020 paper to really have an impact on cold events in North America. And what it is at the beginning, I showed you how we can have Rossby wave activity enter the stratosphere, and then we get wave breaking, and then the stratospheric polar vortex might break down. In this case, you can think about this very similar. We have Rossby wave activity enter the stratosphere. Instead of easterly momentum being deposited in the polar vortex to break down the vortex, we have a reflection that actually takes this wave activity, and the flux is pointed back downward. And so we actually get this wave reflection occurring. It's the momentum, the easterly momentum that might be associated with these waves, instead of being deposited in the stratosphere, enters the stratosphere and comes back down. And then we have this wave activity flux convergence at the tropopause. And in the 2021 event, we actually see that this is what happened. And it's not as pretty. This is a single 2-day wave activity flux cross-section. It's not a composite of 41 events. But what we have is a wave source over Siberia. We have wave activity flux into the lower stratosphere. We have a reflection of this wave activity flux. And then we have convergence downstream. And so you can see that, yes, there's a horizontal component. We have downstream development at the tropopause layer, but we have this added component coming from this wave reflection event. And associated with that, here you're looking at the 50 hectopascal geopotential height. our wave source over Siberia, and as we see, as this animation goes through time, we see the troughing over North America amplify. That's associated with the convergence of wave activity. So this is the 2021 event, and there was this wave reflection associated with it. I said 2020 also had a similar setup. 2020 was a strong vortex period, and we can actually see this in an animation of, these are, essentially this is your ridge, Rossby wave ridge, troughs, planetary scale wave 1 structure. And what we see as we go through this is this upward and then reflected wave activity, and we see the amplification of a trough over North America. And one of the key indicators for having one of these events is a negative shear in the upper stratosphere that can be measured by, as a proxy, the difference between the zonal mean winds at 2 hectopascals and 10 hectopascals at 60 So, how frequently is this involved in cold air outbreaks? Well, we wanted to see if this was a common pattern of stratospheric variability. And as we were looking at this, we were trying to identify these common patterns of stratospheric variability. We looked at this 45 to 75 degree north cross-section, and we took an EOF and cross-section space. So this is from the daily composite of these cross-sections. And what we found is if we look at the first 6 EOFs, we see common modes of variability in this vertical Rossby wave structure between the troposphere and stratosphere. And we see some common modes of variability, but when we get to EOF 5, now there's not a lot of variability there that is described, it's only about 4% of the time, but that's what we're looking for. These cold air outbreaks don't happen all the time, but EOF 5 is interesting. So let me get to that. We look at the coldest days in Chicago. There's 12 of the coldest days in Chicago. Found the coldest day of the year. These are all days where the temperature is less than minus 10 degrees Fahrenheit for a high. So there's a collection here. Maybe some of you experienced 1 or 2 of these. But when we composite all of these days in this cross-section space, and we go back in time, we can start to see the signal of this wave reflection event. So as we go back from day -1 from these cold days to all the way to day -6, we can start to see the development of one of these wave reflection events. And it turns out that, let's focus on day -3 here, this signal looks very similar to the EOF 5 pattern. And what we did was we quantified this. We said, okay, on all these cold days, what are the values of all of these EOFs? And it turns out that EOF 5 has the largest signal, and these other modes of variability tend to be smaller. Now, if you look at each one of these events individually, it turns out that they're always small. It's not their average to be less than 1, they're all small. So the leading mode of variability in this hemispheric Rossby wave structure during these cold air outbreaks happens to look like these wave reflection events. And we can do this for other cities. We did this for Dallas and found the same thing. This wave reflection event was the signal. And so, this is where I want to wrap up. I just want to mention that, thinking about these wave reflection events, this is relatively new, and so there's been a lot of interest in thinking about this. We have to think about not only the vertical structure of the zonal mean winds in the stratosphere, we have to think about sources and sinks of Rossby wave activity. When we're trying to think about whether or not this projects into a, this setup, the way it is now, if this will look similar in a future climate is an interesting question, because the troposphere is warming, the stratosphere is cooling. That impacts a lot of the structures of temperature and wind in a vertical sense. So we might be changing wave reflection layers and that sort of thing. So that's a takeaway here, is that there was an analysis done to look at these wave reflection events in the reanalysis data, and they found that if you look at clusters in which these wave reflection events happen, the frequency of that cluster happens to be increasing in the satellite era. So the question is, what will these events look like in a future climate, given that there's differing temperature trends and that has implications for, from a thermal wind perspective. So with that, that is a overview of lots of different projects I'm working on, but hopefully maybe one of those was of interest to you, and I'd love to sit down and talk about things in more detail. So for a summary, I'll just remind you that we're interested in thinking about extremes with longer lead times, but to be able to act on these longer lead times, we need to know what the windows of opportunity are and when to use these forecasts. And so we're thinking about these and the stratospheric impacts from a variety of perspectives, thinking about vortex geometry, the influence of these tropopause polar vortices, and then common patterns of wave coupling. And so before I wrap up, I just want to mention from a student perspective, and I'll just leave this up during questions, but I'm the current chair, future chair of the AMS Board of Enterprise Economic Development. And this is where this conversation about making decisions and talking with people who are on the decision side of things. The AMS BEAD is called, oversees the AMS Washington Forum. So we are the ones that organize the speakers, and we bring together congressional staffers who are with the people making decisions about where the money goes. And we talk to program managers across different agencies, and we get together with the private sector and the people who are using the decisions that we're helping make. And we get together with academics, all to talk about problems currently across the weather and climate community at this AMS Washington Forum. It's really eye-opening to see how these things are used and to be part of that conversation. The AMS BEAD also oversees several AMS committees, including the Renewable Energy Committee, Financial Weather Risk Management Committees. So there's a lot of really interesting discussions about applications of weather and climate data forecasts. And if you have any interest in joining that conversation as a student, please apply to become a student member of the BEAD. We're looking for students. So I'll end it there.
We have questions? Ian, go ahead.
So when we had the steps 1 through 6, wave activity propagating through the tropopause in the stratosphere, we talked about there being planetary waves that are able to do that. Normally, I guess I think of the planetary waves as being maybe topographically forced, so I would expect perhaps the EP flux to be divergent at the surface. But in most of the diagram, it seemed like the EP flux was divergent at the tropopause, if not even higher than that. So is it, I guess I'm wondering, in those diagrams, is it sort of a stratospheric exclusive interaction that's occurring?
So that is a really, you may not have formed it in the same way, but that's a research question that people are working on. So there's been a lot of research recently to look at how the stratosphere preconditions itself to receive this planetary scale wave activity flux from the troposphere. So yeah, you're right. Topographic waves are happening all the time and being forced in the troposphere. They're not always going into the stratosphere. So if you look at the times when the stratosphere is receptive to this wave activity versus times that it's not, you can see signals in the planetary structures sort of in that cross-section space. And I have figures that I could show you that we can chat about later.
So is it the idea, if the vortex is very strong, trying to think from the Rosman dispersion relation, U minus C bar has to be some threshold and it'll reflect everything away. So if this vortex is strong enough, is it just protective, self-protective?
Yeah, and that's pretty much what happens in strong vortex events in the southern hemisphere, which is why we don't see as many SSWs in the southern hemisphere.
Cool. Thank you.
Brad.
So I have two questions. One, for the tropopause anomalies, are those, it seems like those are very similar to when you get Rossby wave breaking filamentation, then you get these little vortices that blow up at the tip of that. Do they start from that? Or they?
Great question. So
Or they
that is
question-
still
Okay,
a question. That is a source for some of them.
okay.
What fraction has the genesis that way is still, no, it's not understood. But it does seem like that sort of fracturing or breakup or deformation that takes one vortex and splits it into two might be part of the story. Whether or not it's Rossby waves all the time or just internal sort of high latitude forcing, that's still, but yeah, that's a question. The maintenance is definitely radiatedly based. The genesis is probably dynamics, but it's not, hasn't been out there. It's not out there in the literature yet.
And the second question is, have you looked at differences between wave 1 and wave 2 warnings? Because it seems, probably most are wave 1s, and that gives you the Siberian response.
Yeah.
And do the wave 2, do they contribute more to these North American cold air outbreaks?
So, yes, but you can have a variety of different impacts as you progress through the times. So it can be a wave 1 force that really kicks off the SSW, and then later in the progression, wave 2 can come into play and sort of have an impact in breaking up the remnants of the vortex. So sometimes you'll see little vortex pieces meander over North America or Siberia, but that's after the initial wave 1 disturbance. Yeah.
So, quick question. So, we were talking just this last part about the EOF 5. It explains, not a big variance, but still a decent amount of variance. I was wondering that if, even though with the variance, instead the UW-AOS rates is super high, if it actually explains a disproportionate amount of extreme cold air events, like if it's actually super close and other things, if it really is a big chunk of what you see as in the extreme cold air outbreaks.
That's a good question. So one of the reasons that I presented it in the way that it is because this is something that we're working on.
Mm-hmm.
So I would love to talk to more people about it and see if they have ideas and sort of things that we should look at. So yeah, I don't know the answer to that.
Okay.
But it's possible, yeah.
Okay, cool.
There's a comment from Matt Hitchman online. He says, and I think it's more of a comment than a question, but he says maybe a strong vortex tends to reside over Siberia with an Aleutian high over the North Pacific, so TPVs may occur more in the eastern hemisphere when there's a strong vortex?
So that's a really good question. One of the things that we've started to see is that the vortex strength can also impact the size and amplitude of the TPVs underneath it. So this is something that we're still working on, but the various characteristics of the TPVs themselves are different during strong and weak vortex events, even for the TPVs that are underneath the vortex itself. So yeah, TPVs seem to migrate with the vortex, but there's other impacts that are also impact strength, amplitude, circulation around the TPVs, and that sort of thing.
Oh.
I think.
Oh,
Andy,
Angela,
okay.
sorry. Go ahead.
Okay, I was trying to think about how to ask this, because earlier when we were talking about observations for the TPV part of this. I was kind of fixated on this last piece about how none of the models did a good job forecasting the cold air outbreak, but you think it's related to this feature, this reflection. So my question for you is, do you think it's missing something? What observations maybe do you think will most help capture that feature that might help with that prediction? And do you think that maybe that was the deficiency of the model, that it's just not capturing this observation that's really needed?
So that's also, if you look at some of these S2S models, so I showed that one of the metrics to understand if you might get wave reflection was thinking about the difference between zonal mean winds at 2 and 10 hectopascals. Some of these S2S models don't even have a 2 hectopascal layer, so that's a huge deficiency. But other times, even if they do have that layer, a lot of models use a sponge layer where there's wave damping and there's other impacts that might impact just the structure of the zonal winds in the stratosphere. But there's a lot of variability in thinking about what's going on in not only the zonal mean winds, but the shear of the zonal mean winds It's sort of this derived quantity that you have to get right to be able to resolve these wave reflection events. So yeah, because they're sort of this newer thing that people are looking at, there's really not a lot of thinking about it from a sort of predictability perspective. But I did show, so those negative heat flux events that we looked at in that sort of, we can only predict these on synoptic timescales. There tends to be wave reflection events in those. It's not exclusively wave reflection events, but that's one of the things that we're looking at. So many questions.
Go ahead.
So I guess on a related question to that is, I guess I'm interested in the fact that for the 2021 and 2022 outbreaks, that those particular outbreaks weren't forecasted. And I remember in December 2021, I believe, they were forecasting a sudden stratospheric warming to
Yes.
occur in the next month or so.
Yeah.
And I wonder whether you're just setting the bar a little too high for the specificity of it occurring at a specific location. Do you see like when these are forecasts, do they happen anywhere?
No, that's also, so the geometry of the breakdown of the vortex is important. So where do you have the little pieces of the vortex meander to can impact the tropospheric impacts. There was an increased likelihood of cold air outbreaks somewhere in the northern hemisphere, but the where was the question. So that was, yeah, so.
But I think, in terms of that previous question with is it a deficiency in the models, or is it a deficiency in is it an observational
Right.
constraint on our initial conditions? Like the specificity of the location may just be due to
Yeah.
random evolution of wave activity that
Yeah. No, and
you can't predict.
that is probably a large chunk of it, but sort of where are the constraints and where is what can we and can't we predict is still sort of a question. Yeah.
And I guess the question I have is like, when these things are forecast, do you actually see, like, if you got rid of the box of where they should occur,
Yeah.
and say, okay, a cold air outbreak, quote, is forecast, period. Anywhere in the northern hemisphere, does that actually occur? Are those predictable?
I don't think I've seen that question specifically. But generally, when you see an SSW forecast, there's still a question about whether or not the impacts will make it to the troposphere. So that's question one. And then if the impacts make it to the troposphere, from a zonal perspective, where will the impacts be? And a lot of times, if they do make it to the troposphere, you do see some sort of cold region, whether it's Central Siberia, Europe, North America, you do see a cold somewhere, but the where is, yeah.
Just a comment tagging on Angela's question on observations. Have you considered radiostations for looking at some of these events? Because we can actually go up high resolution, especially around 10 hectopascals or 800.
So that was one of the reasons that we were specifically using the NASA MIRA reanalysis to do a lot of this. We haven't gone into, doing a lot of modeling studies. We've been using the data that's available through the operational centers that contribute to the S2S project, which do incorporate a lot of those satellite radio occultation. So I haven't specifically looked at it, but I know that it's part of the operational modeling. But yeah, no, I'm interested in talking more about observations, so yeah, definitely.
I'll just ask one quick question. Oh, wait, there's somebody else? Okay. Andrea, I noticed your map about the increased frequency of TPVs in the eastern hemisphere when you have a weak vortex event. Can I recreate that right in my head?
Yes.
How many are weak vortex events biased toward the month of March? Because you're only 6 weeks, on March 1st, you're about 6 weeks to the end of the season anyway.
So
Or is that not the case?
the SSWs that were included needed to occur at least 20 days before the final warming event.
Okay.
If they were the final warming event, there was no recovery of the stratospheric winds to westerly, then
Yeah.
they weren't included in that.
Okay, thanks. Okay, can we thank our speaker again for